I'm Paul Green. I'm your host. Thank you for joining. And I run a digester biogas RNG advisory business after coming off a career as an engineer, developer, and EPC in this business, and served as a past chairman of the American Biogas Council and was a founding member. I host these free monthly webinars for their educational value on hot topics for the industry. Today's topic is on nutrient recovery and digestate treatment from the biogas RNG projects. You'll get an email from me in 2 days pointing you to my website to download the presentations. So the answer is yes, the presentations are available. They're actually there now. So I'm pleased together that we really have put together some of the top brands in this market niche. So the agenda is here, and so we'll have a very busy 2 hours. And so questions will be in between each speaker. So the end of the speaker, we're going to get some questions as time allows. So digestate nutrient recovery. So the drivers of nutrient recovery are things like the environmental conditions around a project, like direct discharge to surface water, water quality impairment, eutrophication from nutrients, sewer regulations from local wastewater plants, groundwater regulations, so land spreading CAFO nutrient plans, and the farm's need for fertilizers. Here's just a typical digestate analysis of a food waste digester project. You can see percent solids is about 2.4. The VS is maybe 65% of TS. There's some residual organics in there as measured by COD. Some suspended solids, like about 1% suspended, about 1% dissolved. And then, so here's the nutrients. 2,500 total nitrogen, about 80% of that is ammonia, phosphate of 100. So again, this is an actual digestate from a running food waste digester to give us some context. So common mistakes on RNG projects, don't forget the nutrients, right? So people talk about the feedstock and the carbon and the VS and the TS, and that makes the good stuff. That makes the gold. That makes our RNG. But don't forget the nutrients staying behind the digestate, because if you do, the project will hurt. So thinking about nutrient treatment versus recovery. So treatment, a lot of technologies come out of the wastewater treatment space. So you're kind of treating it as a wastewater, destroying the nutrients, kind of hoping they disappear. Recovery is we're trying to capture nutrients in a way that creates a value-added fertilizer that the crop-going community finds to be of value. Some things to think about are price volatility of operating cost chemicals, acids, and caustics, price volatility of recovered fertilizers. So as you make a capital investment upfront in a significant asset, there are some costs that are hard to control. Finding a long-term off-taker on recovered fertilizer for secured price. The fertilizer market has been very volatile of late. The war in Ukraine really triggered some real volatility in prices of things like ammonia. And so trying to make good decisions in the light of that. Material handling and storage is a concern. So your digestate's going to come out 24/7, but sometimes fertilizers are just required a few times a year. So as you recover nutrients from digestate, what are you going to do with them? Are you responsible for them? Do you have partners that can help take up some of the slack? Organic certification is a huge topic. So to be organic, no addition of synthetic chemicals is allowed. Certainly, there's liquid organic fertilizers, solid organic fertilizers, things like aqua ammonia, things like recovered solid pellets and crumble. Organic can sell for a big multiple price premium versus conventional. Also think about applying the fertilizers. So Are you applying the fertilizer directly to the soil? Some plants you can apply directly onto the plant after it's come out of the ground, but certainly want to make sure that it's all compatible. Ammonia is the big one as far as challenges to control and remove. And so understanding the difference between ammonia and ammonium is important, right? So ammonia is unstable and found at a high pH. Ammonium is more stable, found at the lower pH. You can see the spectrum here. So we don't have a presentation today on ammonia stripping and capture, but certainly that's a popular approach. One presentation will talk a little bit about transitioning ammonia from liquid to a vapor phase. So digestate ammonia is about 0.3% nitrogen. But to be a legitimate fertilizer, you got to get it over 5% to get the fertilizer industry to be interested in all of the logistics and the handling of that. So that's a 12x concentration right there. So fertilizers, things like aqua ammonia, you might find them in the 5 to 16% nitrogen range. Sometimes they're stabilized with something like organic citric acid. Ammonium sulfate is another common one where you've got sulfuric acid reacting with ammonia, and ionically you're making that ammonium sulfate, as well as organic ammonium. So as I close out here, just a couple of points. So some things I'm working on of late is the biogas book, the 2024 biogas book, as a rallying point for the industry. Got a bunch of technical discussions in there. I'm looking for some SMEs to help me on some of the creation. I'm developing a bunch of white papers to help. You know, as an industry, where do you go when you want to learn to educate yourself on technologies and system performance? So I see a need to kind of doing more with technical storytelling. I've got some video case studies coming together, but I'm always looking for more project sites. I'm hitting the road in a couple of weeks with my video camera to do some more field case studies in the biogas space. It's a directory. We're bringing in partner sponsors as an opportunity for branding. You can go right now to your app store, whether it's iPhone or Android, and download the Biogas app. And we're building out here in 2024 and 2025, I think, with some new exciting potential for the biogas book. So doing a lot with education of late. So Biogas TV is kind of the brand by which this webinar is coming together. So if you go to biogas.tv, that's a YouTube page where we're populating it with content and things like project case studies. So thanks again for coming today. I see we've got about 140 folks on with us. So Bobby Levine is first up. And so Bobby, the floor is yours. I'll just give a quick bio of Bobby. So Bobby Levine is the CEO of Digestate Organics, a Michigan-based company that specializes in advanced filtration solutions for wastewater treatment and water reclamation. Bobby founded the company 10 years ago and recently oversaw its merger with the Mott Corporation, a global leader of specialty filtration solutions. Bobby completed his PhD in chemical engineering at the University of Michigan, and prior to Digestate Organics, co-founded and sold a company that developed algae-based immune support ingredients for animal feeds and human nutrition. So with that, Bobby, the floor is yours.
Great. Thanks, Paul. Really appreciate it. And thanks, everyone, for tuning in and hearing about digestate treatment. I will start just with a little background on Digestate Organics, so you know where we're coming from, and then briefly some of the benefits and reasons why we're even talking about digestate management. I'll take you through two of our projects that kind of highlight technologies that we use for digestate treatment, talk about where the nutrients end up, and then also look at our fertilizer products, which we brand under our TerraFlow Organics brand name. So our vision and really our mission is to upcycle liquid organic wastes into clean water and value-added products. particularly when we talk about digestate, which is usually on the order of 97% water, 3% nutrients. There's a lot of water there to reclaim in certain areas. That means more than others, but those products also can mean a lot in terms of revenue generation and added environmental benefits. So we do this both for digestate as well as a slew of other waste streams throughout various industries. As a company, we are a full-service engineering and manufacturing firm. So we're based in Michigan. We engineer, design, and then make filtration systems to tackle lots of different waste streams. Today we'll be talking about digestate. And I just want to highlight that we do that in a project management environment. So every project gets a unique project manager that is dedicated to it and looks at all of the unique aspects of that project and what that means both for our customer, which tends to be a developer or an EPC, as well as their customer, which is the farms, the community, et cetera. So really looking to provide holistic digestate treatment solutions. Here's a couple of pictures of our shop. We're about a 20,000 square foot facility in Plymouth, Michigan, just outside of Detroit. As a company, we're about 50 individuals in our unit, and then we merged with the Mott Corporation, which is a larger company based in Connecticut, about 60 years of specialty experience with gas filtration. And so pairing both of our companies together, we really offer a full suite of services, both in the liquid side also. So what we're going to talk about today is really how our platforms can convert digestate into value-added resources and increase profitability in your projects. And it really is in some cases a closed loop where we're taking this manure that's been digested, going through a solution, typically a filtration based, but also sometimes with evaporation and other technologies added on, getting that clean water and that organic fertilizer, and that in some cases is in a loop, right back to that animal. Whether that's water for animal drinking water or fertilizer to grow crops that animal will eat. So really trying to holistically address what a lot of these biogas projects are facing when it comes to nutrient management. A couple of the benefits, and really the reason why you would do digestate treatment and not just land apply the digestate, I break it into financial, environmental, and social benefits. I just want to highlight on a couple of these because Paul already mentioned this. Obviously, there's reduced hauling and spreading costs. But something that fewer people know about is that if we actually treat the digestate and remove volatile solids from it, we can improve a project's CI score because the model assumes a certain amount of leftover organics that are our lagoons sort of stored and still release methane. So we've actually quantified that and can help customers evaluate the impact of that. Obviously, if you can sell fertilizer, that's a huge value add to a project that might not have had that before. I think we're also seeing a change in mindset where if you can tell the feedstock providers that you can reduce volume, so if a farmer gives you 100 gallons of manure and you only give them back 50 gallons of digestate, they're willing to pay for that in essence. And that can be a big part of the economics of how a project was run. And then there's also new water and nutrient trading credits, which in certain areas will allow you to, again, get some financial benefit from that. Environmentally, I think these are pretty obvious. We are able to reduce excess nutrient loading if we are applying concentrated fertilizers instead of dilute digestate. We can do it in a more targeted way to increase crop yields. So farmers are not facing a full lagoon where they have to land apply, maybe in the winter or some other time where it's just not ideal for crop uptake. And then socially, I think as some of these projects get larger, it's really important to think about the community aspect. There's almost not a single project that doesn't have some negative article about, some community meeting, too many trucks on the road, new odors. This is a way to show that you're taking the community seriously around, especially on these hub and spoke projects, around the transportation of feedstock in and out and how we can improve the overall outcome for all the participants in a project. There are kind of four main types of digesters that we're working with today: dairy, swine, poultry, and food waste. I think each of them have some unique characteristics I just want to highlight. So when you think about some of the solutions we offer and the projects you're running, you can think about what makes the most sense for you. So dairy, some of it tends to be pretty dilute, so it's costly to haul and spread. But when we look at the two case studies I'm going to show you, one makes a liquid concentrate that has almost all the phosphorus in it, and the other makes a solid concentrate. And some sites are set up to handle solids, and some are not. Some just have lagoons. And so that's sort of a major consideration when we think about spreading throughout the year. In swine, we see a lot of large covered lagoons that get cold in the wintertime and don't produce gas. But if we want to process digestate year round, how do we do that in a way that preserves those volatile solids so that the gas revenues don't suffer? We have a solution for that. And then we also see that they're facing nitrification and denitrification costs from existing treatment programs that we can overhaul and actually use the nitrogen to make a fertilizer instead of just paying a bunch of money to put it into the air. Poultry and to some extent food waste are unique in that they tend to come in with a really dry feedstock. So some of this poultry manure litter can be 40–50% dry matter that requires dilution. And so we can help by you're adding a liquid, you're going through the digestion process, you need to pull that liquid back out, typically remove the ammonia and reuse the liquid because you can't afford to dump in fresh water and then haul away digestate. So, and that, again, sometimes with food waste can come in pretty high solids as well. So something to think about in each of these types of feedstocks and something that we have solution sets for. This is the entire slew of equipment and unit operations that we provide. We're not going to go through this in detail. Instead, we're going to focus on two main case studies that highlight several of these technologies and how we put them together to treat digestate. So the first technology platform I want to talk about is it's sort of what I call our all liquid platform. Basically, all of the concentrates of the nutrients are in a liquid form. We're not making a stackable solid anywhere. So this is our BC Organics project in Greenleaf, Wisconsin. Dynamic is the owner of this project. And it is designed for 720,000 gallons per day of pressate. So they're digesting dairy manure. They are screw pressing. And then we get the liquid pressate from the screw press. And we are designed for 50% recovery as clean water back to the farms or to be river discharged. And the technologies we're using to do that are a stainless steel ultrafiltration system, which is a tubular membrane, superfiltration, which is a tight ultrafilter, very fouling resistant chemistry, and then a unique process for reverse osmosis that is, we call it sub-induction time reverse osmosis, but it's a sequencing batch style process to help boost recovery and lower energy costs. And then we polish that water with biofiltration. So the key, this whole platform, again, was designed to keep all the concentrates liquid, was designed so that everything could be pumpable and easy to move back and forth to the farm. And then was really targeting volume reduction for these farms. So I have pictures, but I also thought if this video will play, we could just see the equipment as it is at the farm. We'll sort of narrate here as we go, but this is the facility. It has 16 large digester tanks that are 1.3 million gallons each, processing, close to 1 million gallons per day of the raw manure coming in. This building here in the floor is where the water treatment equipment is. They're using burger presses to create liquid pressate and then around 135 tons of fiber per day. This is just upstream of our process. This is pretty common to create a bedding product. They're actually then running that bedding product through rotary dryers to create a sellable bedding product for nearby farms to purchase. And then there's some excess product that is also produced. So this is our facility called the Nutrient Concentration and Water Reclamation System, again, comprised of these multiple filtration unit operations. This is looking here at the ultrafilter, the main first step in the process that is taking the pressate and removing suspended solids, which is principally all of the phosphorus. So the first step here on the way to the ultrafilter is actually some grit removal. This is just to help remove sand and abrasive particles before going to the filters. This is a non-powered like hydrocyclone approach. These are the stainless steel ultrafilters. Again, we're seeing 90+% phosphorus and organic nitrogen removal in these, producing a clear amber colored permeate. This is a picture of what the permeate looks like. And again, so there's this, it's transparent. You can see through it, and we've removed all the pathogens and the phosphorus. This is what the superfiltration looks like. So these are spiral wound membranes. And again, they're doing a tighter cut. So it's sort of like a second stage of ultrafiltration, but with a very tight ultrafilter membrane to get lighter colored permeate that'll then go to the reverse osmosis system. So this is the high pressure reverse osmosis system. So it's actually two ROs in the project. The first is high pressure. This is concentrating all of the ammonia and the potassium into a concentrate, a liquid concentrate, and then making clean water, which you can see here. And then that clean water is put through a polishing RO at low pressure to just do a final polish that's another, 90+% removal of various contaminants, including ammonia, to make our clean water product. And then as a final step on the way to the river, they go through biofiltration towers. These are packed with a small plastic media that bugs are growing on that can nitrify the ammonia, remove any trace amounts of organic matter left, and then send that water nicely aerated through our ultraviolet disinfection system and out to the river or back to the farms for reuse. They have need of it for irrigation, like in warmer months. And then here is a goofy video of me drinking the water on my last trip there. We have a Green Bay Packers tap for anyone who's interested. Actually tastes pretty good. And then these are just the kind of a shot of the materials as it's going. So you can see it starts with the digested pressate on the left and gets clear as it goes. All right. So I'll zoom through these pictures just so when you see it online, you'll have access to some of the pictures instead of the video, but that video is up on YouTube as well. So another picture here, I'll give you a little bit of insight into how the project is running. We are regularly producing water. We are discharging to the East River under an NPDES permit. So we worked closely with Dynamic to help them get that permit. And that's working really well. And so is sending that water back to some of the local participating farms. And then the concentrates are collected, and some of the farms are piped back, some are trucked back to the farm. This is a picture of our operator and an employee from Dynamic actually witnessing the river discharge where it falls into the East River. Some of the learnings I think I want to highlight for people here that we've seen bringing online this large plant, really the largest that we're aware of that filters digestate at this scale, is that there's lots going on in our project, both with different unit operations as well as upstream. So how are the screw presses running? How is the dryer running? If the dryer goes down for 2 hours, then we have to shut off the screw presses, and then we don't get pressate. So I think we are learning about how to balance those different operations with potential upstream upsets, and where would we have rather had bigger tankage to allow for continuous operations while there's upsets and things like that. We have probably smaller tanks than we want between different buildings and different operations, and I think that's something that will take the future projects just to think about for you when you plan your operations when you have lots of steps dependent on each other. Something else I'll mention is temperature management. So our NPDES discharge permit requires certain temperatures for every month. And interestingly, in the winter time, as many of you know, the digestate is right around 100 degrees Fahrenheit, loses a little bit of temperature on its way to our building. We add a little bit of heat to it as we filter it. We actually need to chill that clean water before it hits the river because it is too hot. Our water's coming out warmer than the discharge permit allows for. So obviously there's lots of ways to do that, whether it's geothermal or air-cooled chillers or things like that, but it was a requirement sort of outside of our scope, but something that we had worked with Dynamic on that we didn't realize was going to be as much of a problem as it is. So we are still working on the most cost-effective way to chill this large quantity of volume to get that to the river under the specifications of our permit, and having really productive conversations both with Dynamic, with the regulators, on how to make that work, and we've got some good solutions for that. But something that's just sort of we'll take forward to future projects. The final 2 points One is on the biofilter. We are a fully mechanical process, right? Up until the biofilter, and then we're relying on those bugs to grow and to do their job. And they are doing that, but we, had one instance, just as an example, where an operator accidentally left a pump on, probably very negatively impacted the biology for a brief period of time in the towers, and it took time for that biology to come back, as it does in any biological wastewater treatment process. But that was different than one of our ultra filters, which is made out of stainless steel, and if it gets dirty, you clean it and it's back up and running in an hour. And so I think we had to plan a little bit better for that and understand the ramifications of human mistakes and redundancy and things like that. So a good learning for us as we paired that biological process at the end of the line with our mechanical filters. And then the other thing is staffing for 24/7 operations. Because we're discharging, we do need certified operators, and we need to understand when they're going to be available and not. And it's just a tough environment, I think, in lots of industries right now to hire good operators and to have enough of them to cover the operation. So that's something that we're working on with Dynamic. In terms of next steps, we're continuing to do a lot of work to optimize the process. I think there's lots of low-hanging fruit, whether it's turning down certain pumps to save electricity and without sacrificing throughput, or seeing if we can reduce cleaning frequency of certain membranes to get, again, same performance, lower cost. So we're doing a lot of that work in partnership with Dynamic now. And then as we'll talk about later, we're going to be looking at putting a fertilizer plant on this project to basically harness the RO concentrate and turn that into a sellable product. So it's a revenue stream that's now, again, sort of just left going back to the farms, but because there's such a premium on the organic fertilizer, per pound nitrogen, it makes tons of sense for us to capture that. All right, so our second project is also dairy manure, but this is like a solid platform where we're going to take the phosphorus, and instead of putting an ultra filter in this project, you'll see that we have a digester here on the left, we have a screw press, and we are going to a different piece of equipment that we call our solids removal and dewatering unit, or SRDU for short. And this is a unique technology. I'll show you some pictures in a minute, but we're trying to get most of the phosphorus into a stackable solid on a concrete pad. The liquid from that will go through similar filtration steps as you saw before. So we'll super filter, we'll do our high pressure RO, and then we're actually going to evaporate the RO concentrate, producing clean water, as well as an evaporator residue. And the key to this project, and the reason Bencourt Dairy came to us looking for a solution, is because they needed salts out of their manure. So they've been applying manure from tens of thousands of cows to land for a long time. There's too much salt to the point that crops will not grow well. And so this project was all about volume reduction and salt removal. And so basically all of the salts are now in this small volume of evaporated residue. So we took 300,000 gallons per day of pressate coming out of the screw press up here. And we turned it into 15,000 gallons per day of evaporated residue, which they can compost. They can apply to compost piles that they already have, or they can continue to evaporate naturally through evaporative lagoons, or as you'll see, we can turn it into actually part of our sellable fertilizer product. So a very exciting project for us. This is actually being built right now. I don't have a lot of pictures, but I'll show you some pictures of the technologies. But we will be running this plant later this year. Very high water recovery here. So here we're at about 88% water recovery. So this platform, because it makes a solid product up front, and it uses an evaporator at the end, we are much higher than the 50% recovery of the first platform. So water recovery is really important. This is interesting. And again, the benefits are really around volume reduction, salt removal, and then making a compostable high phosphorus product. So this is what the SRDU looks like. It's a unique system to get compressed air and very unique high molecular weight polymers into the digested pressate, flocculate it, float it, and then press it to make the cake and a clarified digestate. So we have a unique partnership with a company that makes the specialty polymer. We have this technical solution that involves these high efficiency mixing heads, which are sort of seen here at the top of this picture, and then a multi-disc press. And so we put these pieces together to create the SRDU, and it's been really successful for us in terms of getting very efficient separation of the solids. So this is dairy manure during a pilot in Wisconsin, actually. So you can see here, this is the flocculated floating solids. Again, this is containing most of the phosphorus, and then this is the clarified liquid. This is an example of what that cake looks like. Nice stackable cake, usually around 20% solids. This is a lot of data. What I'm trying to show here is concentration and what we remove in the SRDU. So if you just look at like total solids, total volatile solids, and phosphorus, this column shows you the pressate concentration, and this shows you the SRDU effluent, so that's the clarified liquid, and this is the wet cake. So again, if our pressate comes in at 4% solids, it probably leaves around 1.6% in the effluent and 20% in the cake. So that's the kind of concentration we're doing. And in terms of volatile solids, we're seeing about a 75% removal. And this goes back to that CI score I was talking about, where if you if your project today is just evaluated as digester plus screw press, or even digester plus centrifuge, we can use this technology to remove 75% of the volatile solids. And that will result in like a 10 to 20 point CI score bump, which we've had verified by third parties. So that's one interesting thing that this does. And then the second is remove about 84% of the phosphorus that is present in that pressate. So very high removal rate on phosphorus, also on organic nitrogen and suspended solids, and sets you up well for then downstream filtration. But if you're a project that all you need is phosphorus removal and you want a little CI score bump, bolting an SRDU onto what you're currently doing can be really advantageous. All right, so I want to end here in my last few minutes talking about fertilizers. There's a lot of excitement about fertilizers. Like Paul said, Digestate contains nitrogen. Usually about 60 to 70% of that nitrogen is in the ammonia nitrogen form. That's why we're talking about ammonia. You know, interestingly, when that digestate sits in the lagoon for half a year before a farmer uses it, a lot of that ammonia is actually lost. Like it just goes into the air, it causes air pollution, doesn't do the farmer any good because it's gone. We want to capture that before it gets to that point. Obviously, this brings a new revenue source to the farm. And, you know, if you look at the organic industry today, organic farmers really struggle to find cost-effective nitrogen that has high plant availability in year one. They're using a lot of pelleted products that are mixes of manures and compost and things. And they have nitrogen on the label, but that nitrogen isn't actually available for a long time, sometimes years. So it's just a very slow availability. We want to deliver plant available nitrogen out of the gate. And then finally, some of the organic sources today, not only are they expensive, they have regulatory limitations like Chilean nitrate, for example. And it complicates how growers can then distribute that product. You know, Canada has different regulations than we do. And so it'd be great to have new sources. So we saw this in about 2 years ago. We created TerraFlow Organics. So it's a wholly owned subsidiary. And our purpose here is to help create value from Digestate by producing nitrogen-based fertilizers. So we have two kinds of products I want to talk about. The first are aqueous ammonia solutions. So if you're not familiar with fertilizers, they're usually labeled with their NP and K. So we have an 800 and a 1600 product. They look and handle identically. They look like water. They have no salts in them, but they are volatile, like Paul said. So we're at high pH, and they need to be treated the way a farmer would handle conventional aqueous ammonia. So that means it's tilled into the ground, it's diluted and distributed through drip tape. It's not center pivot irrigated into the air, for example. So it's nothing new for agriculture. Farmers have been dealing with ammonia, even anhydrous consideration as sort of new to organics. And obviously both of these are only listed. So they are certified today for use and are sort of ready to go. So we've crossed that hurdle, and we've created the two concentrations so that buyers have options. Obviously, it's less expensive, per pound of nitrogen to move the 1600 than it is the 800, just because of the concentration. The other product I'm really excited about is our 605. This is what I call a concentrated digestate. So we have used our filtration systems to pull out water. We've used an evaporator to pull out more water, and now we're left with a 6% nitrogen product that also has quite a bit of potassium. It's usually actually a little bit more potassium than nitrogen. We label it 605. It often tests more like 606 or 607. It is it's a dark liquid. It has about 50% total solids, which is sometimes surprising to people, but it still has very low viscosity. So it still pumps like water. But those dissolved solids are partially the nitrogen, but partially, the potassium and all the other salts that were in the digestate. We make sure it's screened so it won't clog any kind of drip systems or nozzles, but it is pH stabilized, and that's the key. So it is between pH 5 and 6. We are not adding any unique additives like citric acid, but we have developed a process that allows us to stabilize it and keep it 100% plant available nitrogen. So this, again, for certain projects makes a lot of sense because it takes all of the nutrients that are in that RO concentrate and sells them. Whereas when we make the aqueous ammonia solutions, we're using a thermal distillation process, but we're leaving all the salts behind. So the project still has to manage essentially like a strict RO concentrate stream that contains the potassium, the sodium, and the other salts. And in certain cases, that's no problem. In other cases, it's not advantageous. So just something to think about when you think about which fertilizer makes the most sense. Here's just another picture kind of showing you what a dairy manure digestate looks like going through our process. One final thing I want to end on, if I just have one extra minute. A lot of developers are interested in these hub and spoke models, but they have dilute manure or they have manure that's really far away from the digesters. And so something I think we can also offer is a filtration solution that actually concentrates the volatile solids in the feedstock prior to digestion. This also does concentrate the phosphorus and the organic nitrogen. We use our ultrafiltration for this or our SRDU for this, but just wanted to say that that's another technology that we are offering the industry. We have some cool videos on YouTube. Paul's been great about putting those up for educational purposes, so definitely check that out. And if you have a project, we would love to talk to you about how we pilot. So we have a significant pilot program that involves either samples coming to us in Michigan or equipment coming to you wherever your project is. And it's a big part of how we get to start working with a client and then also show them with their exact digestate or their exact manure where nutrients partition and how best we can serve them with different technologies. So I will stop there and see if there are any questions.
Yeah, there are some, Bobby. Thank you. Nice job. So the concept about CI score improvement is getting some traction. And so I'll read this. Why would nutrient separation improve CI score by removal from digestate? If they're volatile, was the digestion process inefficient? How much would separation improve the CI score approximately?
Yeah, so typically what we've seen is that the standard model being used, the GREET model, assumes that the digester and the screw press, let's say, leave volatile solids in the digestate. The digestate's going to an anaerobic lagoon. Some of that is still resulting in methane and evolving into the atmosphere. If we remove more volatile solids than what is estimated in the model, we get a CI score improvement. Like I said, it's usually between 10 and 20 points, and it depends on the climate. So because more degradation happens in warmer climates, it's actually a bigger CI score improvement in warmer climates. But it has nothing to do with the nitrogen or the phosphorus. It just has to do with the ability to remove additional volatile solids after digestion through our processes and then keeping those volatile solids aerobic. So if you do the SRDU, let's say, or the UF, you remove 80-90+% of the volatile solids. You can't put those in an anaerobic situation, but if you do the SRDU, it's natural to compost that material or land apply that material, and then those volatile solids are not degrading anaerobically.
Thank you. So lots of questions coming in, but we're right on time. So we may need to be addressing some of these by email afterwards. So Paul at green-tech.com will get to me and I can distribute accordingly. But thank you, Bobby. You're doing some amazing work. So appreciate it. So next up, we've got Sarah Van Tassel with Cedron. So Sarah, you're there. I see you. Okay, wonderful. So Sarah Van Tassel started with Janicki Industries after graduating from the University of Idaho. Initially, Sarah established Janicki Industries R&D lab before moving to the Aerospace Design Group. Sarah then worked as program manager on alternative energy projects such as wind, solar, biomass gasification, and scaled composites, Spaceship One, and others. and did some work with the Bill and Melinda Gates Foundation, leading to the formation of Janicki Bioenergy, now Cedron Technologies. Sarah transitioned to her initial role as president and now is chief operating officer. In these roles, Sarah drives technologies development, including the VAR core. So thank you, Sarah. The floor is yours.
All right. Well, it's great to be here. Excited to talk to you guys about the VAR core. Before I talk about the VAR core, just a bit of background on Cedron to give a bit of grounding as to who we are. So we were founded about 10 years ago, but we have a longer history than in that. Much of our leadership came from our CEO and founder's other company, Janicki Industries, which is about 30 years old. Janicki Industries is a technology leader in the aerospace and composite world. And we like to say that if you see anything in the air, whether it's private, commercial, military, whatever, Janicki Industries played a role in the technology development of that piece of equipment in one way or another. And that same technology development DNA is at Cedron. So Cedron's a engineering-centric company, and we like to innovate every part of the business and be quite vertically integrated. So we invent technology, we do all of the detailed mechanical, electrical, chemical design, we design our manufacturing facilities to make that equipment ourselves and make it inexpensive. We build all of our electrical panels, we write all of our controls, and then we also go as far as developing the projects, installing our equipment, and then operating our equipment long term. So we don't actually sell our technology, kind of own the business holistically and provide it as a service. Apologies, I got a cold and my voice is struggling, but I think I'll be able to get through this. So the VAR core, though, that's what we're here to talk about it relative to Digestate. So the VAR core system, it's a holistic liquid waste handling system. It combines dewatering, drying, distillation to take in a wide variety of waste streams and separate them into beneficial reuse components, depending on what is in it coming into the VAR core. And also to create a clean water that can be used for many purposes. At a super high level, what the VAR core does, it's taking in the liquid waste and it sends it into a dryer as the first step. In the dryer, the waste is heated up to boiling. So all of the liquid leaves and you're left with a dry solid that's pathogen-free, it's seed-free, weed-free coming out. It's typically going back to Bobby's comments on the NPK, it's about a 3-3-3 product if what is coming in is digested manure. So that's a fertilizer product, pathogen-free. The vapor that leaves, we send through a compressor, and it is now at a higher pressure and temperature, and that is sent to be used as the energy source for the drying of additional incoming waste as that steam is condensed. And then that saturated liquid is sent through a stripping process where we separate the water from the nitrogen, ammonia, so that you're left with these three outputs: the dry solids, a nitrogen fertilizer. This is a 10-0-0 stabilized pH neutral fertilizer, and clean water. The backbone of the technology, because we do use a thermal mechanical process, which a lot of people's gut reaction is, wow, that's a lot of energy if you're going to be evaporating 1 million pounds of manure a day. But we use mechanical vapor recompression, which is much more energy efficient. So just a very, very basic overview of how it works, because we get a lot of questions about this as people try to wrap their minds around what we're doing. You take a kilogram of water at ambient conditions and turn it into steam, your gut reaction is right. That takes a lot of energy. So it's about 2,400 kilojoules for every kilogram of steam that you evaporate. If you then invest a small amount, about 50 kilojoules of energy, you buy electricity to run a compressor, you now have that same steam at slightly higher pressure, so at about 1.5 bar. Now, if you recondense that, you can get that 2,400 kilojoules back. And if you look at draw a box around the whole thing and look at a first law balance, you took water from 20 degrees to 30 degrees with ultimately only investing 50 kilojoules of energy. But in the meantime, you got to go through multiple phase changes and do all these clever things to separate the different nutrients and components into beneficial buckets. And if you look at that, a VAR core compared to traditional natural gas boiler with just direct drying, we're about 30 times more efficient. We are doing 15 megawatts of thermal energy transfer in the VAR core, but we're only investing 500 kW. Quick overview of what is happening within our evaporator. So this is a cross section of our evaporator. And if you can picture a hub that's about 2 to 3 feet in diameter, a hollow hub, about 90 feet long. On that hub, we have these 10-foot discs. They're hollow discs, about 4 inches deep, welded to this hub so that you have this hollow spindle that we're sending our compressed steam inside of. So that is our heated surface. We take digestate or whatever waste stream you're processing, and we pour that slurry onto the disc face to create a thin film on top of the disc. That thin film sticks to the hot surface. The whole spindle assembly is rotating slowly. And as the material comes around to a full rotation, by the time it gets to this scraper, the material's dry and we can scrape this crepe off of our skillet, so to say. And that dry product, because of its time at temperature, it's pathogen free. All of your solids get scraped off and sent out to be managed as a dry product. All of the steam and vapor, ammonia, that would evaporate off gets sent out to the compressor. So that's the details of what's happening within the dryer. The excess material that doesn't stick to the disc face gets captured at the bottom of the evaporator and is sent back in this recirculating direct application system. This is a slightly more detailed process flow diagram to give a little better concept of what is happening. The digestate comes in, it gets preheated up to saturation temperature. At saturation, very few things want to stay dissolved in the water, so things like CO2 that would inhibit heat transfer in our evaporator, we remove in our degas system. That degas slurry then goes into the evaporator where we're pouring it onto the disc faces. The direct application system is recirculating any material that didn't stick to the discs. The dry solids are being scraped off. This is a cross section of the evaporator in the opposite axis. So you're seeing that hollow spindle with discs on it. That dry material gets sent out of the system. The vapor gets sent to the compressor where it's increased at approximately 0.5 bar and then is sent to the inside of the spindle. As it starts to condense, you get this stripping action such that most of the ammonia that's in the product is going to leave in a concentrated form out of the spindle in its own pipe. And the water is going to be stripped of that ammonia and sent out the other end. That water, though, is still hot. It just condensed. So we're able to use that hot water to counterflow the incoming material to preheat it up to degas temperatures. And it also removes the heat from the condensate. Again, like Bobby mentioned, you need to have cool water to be able to send to the environment. So we cool it against the incoming material so that we have this clean water for use at the farm or to send to the environment. The ammonia, we then condense back to a liquid and send to our stabilization technology to generate the nitrogen fertilizer. One of the things about the VAR using this thermal mechanical process is that it's incredibly effective every time and is not susceptible to all of these different, potential variations in your infeed. We don't care very much about particle size because we're not really filtering. We don't care too much about the biology because we don't start out with a front end biological system. Basically, if you send us a slurry, the VAR will do the same thing every time, separating the things as planned. And this just kind of tells that story. So you have a slurry. In our case, we're talking about digestate, but it could be anything. You have water, you have some solids, you have some dissolved solids, you have dissolved gases, all sorts of things in this slurry. Start to heat it up, and what happens every single time you heat something up to boiling is that anything that has a boiling temperature below 100 degrees C, it's going to leave, it's going to boil, and you're going to be left behind with pathogen-free solids. So all your carbon, all your phosphorus, all your potassium, it's going to get left behind every single time, and everything else will boil off. So incredibly effective and robust to do that every single time, no matter what the waste stream. And then if you capture that vapor that now has, again, depending on your waste stream, all sorts of things, water, ammonia, odor, other VOCs, anything that boiled below 100 degrees Celsius at or below. But if you start to cool those products down, they all want to recondense at different temperatures, which allows us to capture them into these separate buckets where we can capture the odors, we can send them to odor control as a point source control. The ammonia also wants to recondense at a different temperature. We can capture the ammonia, we capture the clean water. And again, it happens every time the same way, regardless of what was in it to begin with. This kind of tells that same story, but in a table form and specific to digestate. So basically, we can run an analysis on the slurry and say, okay, what's in the slurry? We've got some ammonia, we've got water, potassium, phosphorus, different forms of nitrogen, carbon. What's its boiling point? And once we know its boiling point, we can say, well, here's where it's going to end up. It's going to end up in our distillate as a nitrogen fertilizer, and we can calculate the volume that we'll be generating. How much water are we going to generate? And what is in our dry solids and at what concentration? This is just some photos of what those end products look like. This is the water coming out of one of our projects in Indiana, showing what that water looks like. The solids, this shows it in several different forms. So this is what it looks like scraped off. This is raw manure actually for this project. So this was raw manure going into a VAR. We create that crepe surface, we scrape it off, and this is what it looks like directly scraped off. You can run it through a grinder to make the particle size more homogeneous, or you can pelletize it. Whatever form factor you want in that end product will put on as a post-processing at the back end of the process. Because we aren't adding anything to this, we're just heating it up and cooling it down. It is OMRI certified, and we have that certification. Again, it's also pathogen free. So that's what our solids look like. And then we create this nitrogen fertilizer. We have it actually certified in two different forms. We have a 300 and a 1000. Bobby already talked about the benefits that this has to farmers. So I won't elaborate too much more, but yeah, being able to have a pure nitrogen fertilizer source that is plant available in year one is really huge. So this is a huge impact to the economic story. Only got a few minutes left, so I'm going to try to go quick. Our core business model is, like I said before, we don't sell our technology, we sell the service. So we build out a project, and then the project gets tipping fees. If tipping fees matter, sometimes we charge a manure management fee, sometimes we don't. In projects that are using human waste or other things, we might charge a tipping fee. But really, on a digester project, the real economic story comes from selling that nitrogen fertilizer and selling the solids. So here's what it would look like at a couple of different farm scenarios. We can take that raw manure in, do grit and fiber removal, and send it into the VAR to make your water, your nitrogen, your solids. Or with a digester, like we're talking about today, you send it into your digester, it does its deal making biogas. We then do fiber removal and we can send it to the VAR after that. One of the reasons that we really like a digester project over raw manure is that the other thing that's happening in the digester is that you're converting a lot of your organic nitrogen to ammoniacal nitrogen. So we actually make a higher volume of this organically certified nitrogen fertilizer, which really changes the economics of the story. So, that's our favorite pairing, is a dairy with a anaerobic digester. I'll go through this quickly. Some of our sites that are up and running. Our first project was a 4,000 cow dairy in Indiana. This is with raw manure. It's been operating for about 4 years now. We process about 40 million gallons a year of raw manure. This was a pilot that we still have. We built it several years ago. We've run it at various sites around the world. So we can ship this. It fits into 2 shipping containers. We can send it to a host site and run small scale testing to show how that product will behave in a VAR. Our first project was that we sent it to a rum distillery in the US Virgin Islands, ran it for about a month there. Currently, it's at our facility here in Washington, and it's running on biosolids, direct biosolids. Like I say, we can run it on all sorts of different products, and we can send it to the host site or test it at our site by sending the waste streams to us. Another project that we have up and running, this is a project in Washington State. It's been running for about a year. We get trucked septage and biosolids from the local community to our facility, and we process it through the VAR. Our dry product gets sent to farm fields in eastern Washington. The clean water goes back to the city. Our next project to come online that's going to start commissioning next month is for a 20,000 cow dairy with a digester in Indiana. So this is taking digestate at about 200 million gallons a year. We have 5 VAR in this building end to end, and we're generating stabilized nitrogen fertilizer with a long-term offtake contract for that. The dry solids are going to be going to local farmers in about a 200-mile radius. And our next project that's going to come online later this year has 3 VAR at a 12,000 cow dairy in Wisconsin. And sorry for rushing there at the end, but I am just at time. So that's the short story on Cedron and our VAR technology related to digestate.
Thanks, Sarah. Great job. Just a couple questions here. As far as OpEx, how do you think the VAR compares to other approaches like membranes? Do you think it's comparable, more or less? Any sense of that?
We've done quite a few third-party evaluations, and obviously the stories depends on what you're comparing it to, but from an OpEx, if you look at the whole story and you're really trying to make all your products of value where they don't need any post-processing beyond that, yes, we find that we are very cost competitive.
Yeah, good. Wonderful. Well, good stuff again. We're tight on time, keeping a schedule. So, Sarah, thank you. Nice job. And VAR, it's extremely cool. I got to get to see one of these days. Those are some great construction pictures. I like that 5 in a row one. That's going to be quite a project. So, thank you for joining. So we've got Fluence coming up here. So, got Jason Bowman with Fluence presenting. So Jason has a BS in physics from UNC Chapel Hill and spent the last 16 years working in the industrial wastewater, water, biogas space. Jason's experience includes developing global process solutions, having been in over 60 countries. Jason currently manages Fluence's industrial wastewater and waste to energy division for North America. So we're excited to hear from Jason about some newer technology to this biogas space. I think it's got some good applications, a good niche. So Take it away, Jason.
All right, Paul, appreciate the introduction, man. That was a tough act to follow. I agree that Indiana operation was pretty impressive. But yeah, just to give everyone kind of a general intro to Fluent. So we're probably one of the biggest companies you haven't heard of in the US in terms of water and wastewater operations. So Fluence focuses on everything that is water and wastewater, both on the municipal side and on the industrial side. So my specific focus is on anaerobic digestion facilities, and the way Fluence operates, as I mentioned, we are a global company. So headquarters is in Minnesota, but we have engineering, design, manufacturing, marketing, other management offices all over the globe. So we're pretty much in every time zone. So what we are here today to talk about is the kind of the digester and digestate side of the business. So Fluence being an anaerobic supplier, so we do the design and supply of anaerobic systems. Obviously, with our wastewater division, we know a bit about the digestate side. So what Bobby and Sarah had talked about was more on the recovery side. So when we're talking about digestate treatment, most of our technologies are focused on the nitrogen reduction, i.e., let's destroy it or convert it to another form that comes out of the wastewater. So what I want to kind of touch base on today is, depending the type of project that you have, food waste, everybody puts it in its own little box, but if you go to 10 sites, you're probably going to have, 10 different, slightly variable digestates. A lot of that depends on the type of digester and how the digesters are operated, but a lot of it depends on the pretreatment as well. So there's a lot of things that impact the digestate side of things, what's coming out of the digester, and we're going to focus a bit on that today. So just to give you an overview of Fluence, we've done a lot of different food waste projects around the globe. More recently, we've put more of a emphasis into the North American market because obviously things are changing here. Historically, as Paul mentioned, I spent the better part of the past 6 or 7 years focused more on a global basis, but given everything that's going in the U.S. right now, we've decided to make more of an effort inside of the U.S. So we operate more like a European model where it's an EPC-based approach, where we do a lot of the engineering upfront and design and assembly in our own factories. So that's both for the digester side of things, but also for the wastewater and digestate treatment side. So understanding anaerobic digestion and digestate in general, obviously, when you get into these big food waste projects, the type of feedstock that comes in impacts your, number one, your digester design, but number two, your digester performance, and then number three, what's coming out, right? When you start getting into, feedstocks that are more, lipid or fat based, a lot of energy generation there. When you get into projects that have more of like simple carbohydrates, things like that, maybe proteins, maybe the energy generation is a little less. So in these food waste projects, that's why a lot of times you see, methane, RNG production going up and down, but also the characteristics of the digestate. So a lot of different, mechanisms, a lot of different feedstocks out there. So, a lot of these facilities have multiple varieties of feedstock. It's a combination. It's not often just dairy or, just a brewery or, just a slaughterhouse. When you get into these larger, cogen facilities, developer-driven facilities, you're trying to get as much feedstock from as many different sources as you can a lot of times. So, understanding what you're getting and how that impacts your digester design and performance is really critical. So, two points here quickly before we get into the nitrogen removal side of things. So there's a lot of different types of digesters on the market. So Fluence, we offer 3 different types of digesters, and we apply these digesters in different situations. When you get into food waste digesters and you have a combination of feedstocks, more often than not, you're going the conventional route with like a CSTR. But there are other unit processes. And the reason I bring this up is they're all operated a little differently. And when I say that, they maintain, they're geared toward a certain COD concentration or a certain volatile concentration or a certain total solids concentration. So the way these facilities come together a lot of times can actually impact what the digestate looks like coming out on the backside. So let's talk about that for a minute. Paul had given us an example of a typical food waste digestate. You know, you have your total solids 2.4%, TSS a little over 1%. You see your COD there, 13,000. So we're going to use this as an example and kind of roll forward with this, how Fluence would approach this type of digestate. And I'm going to give you several examples using the digestate technologies that we have developed. So to put this in perspective, I know there's a lot of engineers on the presentation today. There's a lot of developers, so a lot of different backgrounds here. But one of the common things we run into when we're talking with developers or end users specifically is, oh my gosh, why are these systems so large? And as Paul mentioned, these are highly, highly concentrated. To put Paul's example into perspective, so if this was a digestate with the characteristics that Paul gave, a 60,000 gallon a day digestate flow rate is basically saying you have the same, is the equivalent of like a 1 MGD municipal facility if you're just looking at the organics, or it's the same as looking at a 3 million gallon a day municipal facility if you're looking at the ammonia load. So this kind of helps put things in perspective, right? If you picture a 3 MGD municipal facility, it's large. So you're trying to treat the same amount of loading, even though it's a smaller flow rate, it's the same loading, and you're trying to treat this, in as compact as a space as you can. So just kind of keep that in mind as we walk forward. Putting these things in perspective is often pretty key when it comes to these designs. So there's a lot of acronyms when you get into the nutrient removal technology. I'm not going to go over all these in specific detail, but they will be here so you guys can reference them in the future. And I'm sure Paul will be distributing the presentations or posting them as well. So let's get down to the nutrient removal technology that Fluence has. So on a global basis, we're really known for two types of nutrient removal technologies, and they are shortcut nitrogen removal. So what I mean by shortcut nitrogen is typically when the digestate comes out, it's a little bit of organic, TKN. As Sarah mentioned, it has been converted to like a more readily degradable form. You have your ammonium, if you will. So what we're doing, what these types of designs focus on, is taking that ammonium and converting that directly to nitrogen gas. And so the conventional method of doing that has been a biological method, right? You either have a series of aerated biological reactors or anoxic reactors that are mixed. And what you're doing is you're oxidizing the ammonia to a nitrite, then to a nitrate, and then you're denitrifying the nitrate to nitrogen gas. So there's a lot of steps in between there. So what the technologies I'm going to talk about today basically take that ammonia and skips the nitrate conversion step and goes right to the nitrogen gas. And the reason why that's important is it saves a lot of energy. In conventional treatment, something like 40 to 60% of the energy that goes into these processes is that initial oxidation step when you go ammonia nitrite to nitrate. So by eliminating that one step, you're significantly cutting down the energy in these more, let's say, biologically driven nitrogen removal systems. So all that said, today we're going to talk about membrane aerated biofilm reactors. This is specific to Fluence. It's different than a membrane bioreactor. Essentially, this is a membrane that you're injecting oxygen directly inside of, and through the physical size of the membrane, the pore size, only oxygen comes out. So it's a passive aeration, meaning that only oxygen diffuses through the membrane. And what happens is you develop a biofilm that grows on the liquid to membrane side, and you're directly injecting that oxygen to that biofilm. So it's a much more effective mechanism of creating that initial oxidation step, if you will. The second system that we're going to talk about today is called a nitrosax. Again, this is a nitrogen shortcut removal process. This is a more of a conventional suspended phase biological process, whereas the MABR is primarily attached phase driven, and we'll talk about the difference there. There are two other technologies that we have. One is a more conventional nitrification, denitrification system. We're not really going to focus on that today. We also do phosphorus precipitation and struvite removal. From our perspective, this is more for the preventive side of things. So we don't want struvite or calciums or things of that nature settling out in the equipment downstream. So a lot of times we'll apply like a struvite removal step ahead of the processes that we're going to talk about today to ensure we're not getting any unnecessary precipitation in our biological reactors. So for the MABR technology, again, this is developed specifically by Fluence. I mentioned passive aeration. This is different than diffused aeration, where conventional diffused aeration, you basically have a device that's on the bottom of the tank floor. You're putting, compressed air or atmospheric air through a piping network and through a diffuser, comes out the bottom of the tank. The bubbles are 1, 2, 3, 4 millimeters in diameter, and they rise to the top of the tank, and that's how oxygen diffuses. Here with the MABR technology, the oxygen is directly injected into the membrane, which is where the biofilm grows. The biofilm in these systems are primarily autotrophic. That basically means that it's bacteria that focuses only on ammonia nitrogen. So this is beneficial. Why? Well, it gives the nitrifiers a place to grow, but it's also a much more energy effective way of transferring oxygen to bacteria. So typically when we look at an MABR process, we want a very specific COD to ammonia ratio, and we'll talk about why that's important here in a minute. But essentially what we're trying to do here is create a mechanism, an aerobic process inside of an anoxic process, so that we're getting simultaneous ammonia reduction and nitrate reduction. So it's a much more energy efficient mechanism for removing nitrogen. So if we take MABR to the next level, we have a process called nitro. Essentially what nitro is the MABR process operated under a specific pH, a specific DO, and a specific ammonia concentration. And if we can control these parameters, essentially what happens is you can control the growth rate of specific organisms in these biological reactors. So essentially what you're trying to do is create a mechanism where you favor ammonia oxidizing organisms, but you create a condition where the nitrite oxidizing organisms don't like the environment, so therefore they don't grow. And this is how we shortcut the nitrogen removal process. So we can take the ammonia to nitrite and then the nitrate to nitrogen gas, again, skipping that nitrate conversion step. So big energy savings here. Now, most of the time when we're talking about MABR and nitro operation, it is a high rate ammonia reduction process, but typically the rate limiting factor here is going to be about 100 ammonia on the discharge. So this is important to understand because the systems do a very good job of getting the initial ammonia reduction, but that last bit of ammonia reduction, there are, let's say, more cost-effective ways that this can be done. So this is where a process like nitrosax comes into play. If any of you guys know what a share-in process is, essentially it's a suspended growth reactor. You're trying to promote high activity ammonia removal over nitrate. similar to the MABR nitro process, but this is a suspended growth reactor. So tends to be a bit more, let's say, cost effective for the initial, what I would say is like a pre-treatment step, the initial 40 or 60% reduction of ammonia. So again, what we're doing here is we're controlling the ORP and we're controlling the pH primarily so that we're targeting specific bacterial populations so that we can control the kinetic reactions here. Obviously, digestate tends to come in at a high temperature, so in most situations, we really don't have to adjust the temperature, but we have had some oddballs where, for whatever reason, the digester didn't have heat exchangers or was not operated at a high temperature. So there is a consideration in some cases where we do have to have like a heat exchanger or something to boost the temperature up. Typically, we want to be 30, 35 degrees Celsius as a normal operating point. So just to give you kind of a 30,000 foot overview of the difference between the MABR nitro and nitro SAX process, the main advantage for MABR and nitro is going to be process stability. It is an attached growth process, so once the bugs are there, once they're populated, it's very difficult to lose that population. The disadvantage to those technologies is the COD to ammonia ratio, or the BOD to ammonia ratio, if that's how you prefer to think about it. If the organics are still too high, you run the risk of having too much heterotrophic bacterial population versus an autotrophic bacterial population. Basically, that's a fancy way of saying you lose the bugs that want to remove the ammonia. You have more bugs that want to focus on the BOD. The BOD bugs grow much quicker than the ammonia bugs do. So we have to keep in mind that specific ratio, and I'll talk about how we address that in the upcoming slides. With the nitro-sax process, it's a very simple process, very high rate. Again, it's typically aimed at getting the initial 40 to 60% reduction of the ammonia. So very, very cost effective, very simple. Main advantage, there's no additional chemicals that have to be added typically to the nitro-sax process. Because when we're dealing with these digestates, typically the chemical ratios we need are already present. So I'm going to jump ahead to Paul's example here, and there's a few things that jump out when we initially looked at this and kind of changed the way we wanted to approach the mechanism in which we treat this digestate. So I believe someone else in the questions earlier kind of pointed this out, but there's a lot of residual COD and volatile fatty acids left in this type of digestate. So it might point to, there may be some digester issues, maybe something's going on there. But if we look at that, if we look at this total COD 13,000, and then we look at the ratio to the nitrogen, so we're 5 to 1, excess of 5 to 1 ratio here, and here we're basically saying that the ammonia concentration is 80% of this total nitrogen. So the actual COD to ammonia ratio is actually even higher. So there's a couple things we need to do first. Before we can go into an MABR or nitro process, we want to make sure that the total solids, number one, the total solids have been reduced because these are attached growth processes. So we want to minimize the solids going into the unit. One way to think about it is the less solids going into these units, the more energy efficient the process is downstream. There is a point at which if you have too many solids, it just becomes very difficult to transfer oxygen. But number two, it becomes difficult for the right type of bacteria to accumulate. So that's the first thing we saw. Secondly, the COD, we need to knock that down to roughly, let's say, 3 to 1 or 4 to 1 ratio. So why do I point all this out? So given the COD and TSS, for Paul's example, what we would have recommended is an additional solid separation step, whether it be centrifuge or a DAF unit or something of that nature. We need to try to get the total solids and the TSS down to like the 2 to 4 gram per liter range. The second observation is we would likely want to put in what we call a swing zone, which is a combination of an anoxic-oxic reactor. And again, here the point is we want to focus on that COD. We want to be able to knock down any soluble COD that's left to a point to where we can maintain that 3-to-1 or 4-to-1 ratio that I mentioned. So of all the unit processes that we have here, this just gives you an idea of the potential combinations of the MABR, nitro, and nitrosax process and how the volume would be impacted specific to Paul's example. And then we've ranked these in order of lowest nitrogen removal efficiency and then the highest. So when I say highest here, we're talking about total nitrogen, which is we'd be able to achieve 30 to 40 parts per million of total nitrogen. So at the end of the day, with Paul's example, what we would actually recommend is more of a conventional step in the end because of that TSS and that COD ratio. So what we're looking at is a two-step nitro step process, anoxic, followed by an aerobic reactor. We'd have a nitrate recycle. We'd have a secondary clarifier. With this type of process, we would expect the total nitrogen coming out of less than 40 parts per million. It'd be about 2,500 square feet for Paul's example. Again, going back to the whole page on perspective loadings, digestate versus municipalities. 2,500 square feet in the grand scheme of things is not that large, but it is a biological process. So something like this would be on the order of about 1.5 million design, equipment, and installation with the construction. So I hope that's able to put things in perspective for you guys. So again, 20 minutes, a lot to cover. So hopefully.
No, I appreciate it. Definitely lots to squeeze in. So good, Jason. We'll have some questions for you to mop up for us later. And as we transition over to Brian, there's some online if you want to jump in there and answer some of the questions in the Q&A.
Sure. Sounds good.
Okay.
All right. Thanks,
Thank
Paul.
you very much, Jason. Good stuff. Some leading edge technology there to consider for biogas projects. So got Brian Healy next here. Brian's with Global Water and Energy. So he's got over 30 years in this space of industrial wastewater treatment design and over 15 years working with anaerobic technologies. He's the VP of North America for GW&E. So Brian's going to talk to us here about some approaches for nitrification, denitrification. Thanks. Here you go, Brian.
Good. Excellent. Thank you, Paul. And I assume people can see the screen now.
Yes.
Very good. Very good. Good. Yes. As Paul mentioned, I'm with Global Water and Energy, and we're a company that's been around for over 33 years now. And our focus has always been on food waste, particularly the food and beverage industry. So we've been doing waste to energy projects, not necessarily always energy driven. Some are wastewater driven, but we're dealing with the same substrates, the same feedstocks for over 33 years. So we've got a truly global presence. We've got direct presence here in the U.S. We've been in the U.S. market for nearly 20 years now, and we've done well over 500 complete projects in 68 countries since our inception. So we've been a leader really in the food waste to energy market. One of the important aspects that we bring to the table is really the digestate management, which it really turns into a wastewater treatment project for a better explanation. And so our background has been meeting wastewater treatment regulations for many years, post our anaerobic and aerobic processes. So we got a very good handle on what needs to be done in order to meet your permit requirements and manage your nutrients as well as your residual organics. That being said, and again, we don't typically do manure digesters. We typically focus in the food and beverage industry, and therefore we focus on standalone, food waste energy type digesters. So that kind of repeats some things, but just to kind of give some background on processes. So, digestate is a production. It's essentially the byproduct of anaerobic digestion. Here I'm just showing a small segment of a system. So we would have the digestate or effluent from the digesters. This is a thermophilic type process is what I was working with here on this particular example. So that goes into the digestate holding tank or post digester, which is typically at mesophilic temperatures. We still have some level of digestion going on here and still some level of biogas production. But it's essentially kind of a white spot in the pipe. So it's ahead of your dewatering system. So it allows you to have a dynamic level in this tank. So you don't have to dewater all the time. You can work the level down, during the week, and then maybe in the weekends, you don't have to dewater, Saturday or Sunday, or maybe not 24/7. So it gives you some opportunity to do maintenance down the line as well. So from the digestate, we go again to the liquid solid separation stage. It's typically going to be a screw press or a centrifuge. And then again, that liquid fraction goes on to further treatment, which we're going to focus on. And again, the solids drop out and typically are used for beneficial purposes, bedding, or more often than not as a soil amendment. As Paul pointed out, it's a bit misleading to call it fertilizer because it just doesn't have the NPK levels that are traditional in the industry. But it is a very good soil amendment, not only for the NPK but for other things it brings to the table from a soil science standpoint. So again, looking at aerobic process, one of the things that I'll point out is as I'm focusing on food waste digestion, the level of nutrients are high, but they're still not nearly as high as they are in manure type systems. So the idea of recovering the nutrients is very good and very well proven. But on the food waste side, you're starting with a lower amount, and so the recovery and the costs associated with that, it doesn't pencil out as well as it does with a manure system. So in many of our systems, we go with kind of the more traditional nutrient removal through aerobic nitrification, denitrification, as Jason mentioned. But again, it's a secure and reliable method. If you have problems on the back end, you want to keep things simple, because if you can't get rid of it, you can't bring in feedstock to the front, you can't produce biogas, and you have a problem. So it's kind of not rocket science. It's simple, it's straightforward, and it's proven. Again, it'll ensure your discharge requirements are met, so you can continue operation. And from a CapEx standpoint, it's generally less than 10% of the overall project cost. OpEx, again, can be relatively significant, so you need to keep an eye on that. But again, it's flexible, and you can adjust it OpEx-wise really to meet your permit requirements. And the key is really in these systems is flexibility all the way around. Generally these are greenfield sites. You have somewhat of a understanding what your feedstocks are, but feedstocks change continually, and so you need to have a flexible system on both the front end, which is your depackaging, typically your middle end, which is your digestion, and then on the back end, which is your digestion management. Again, you're not relying on third parties to take off material for either land application or such. But, if you do have an opportunity where you do have a third party, a farmer or somebody that will take your material, you can use this system seasonally, or you can even mothball it as long as you have a contract in place. But the important thing is you have it when you need it. Kind of a simplistic drawing of how this process works. You have the anoxic zone, which is where your liquid fraction, your digestate comes in. We stick in another step here. We typically have a dissolved air flotation system in here to further polish what's coming off of your screw press or centrifuge. Those systems are reliable, but again, they're not perfect. So you do have a certain amount of bleed through of solids, and they will upset. And it's critical to put another kind of belt and suspenders in here to keep that from entering into your aerobic process, because it brings more nitrogen, more COD, and more phosphorus, and so it can actually significantly change your design or cause operational problems. So your nitrification nitrifiers grow here in the anoxic zone. There's communication between the anaerobic and the aerobic zone, which your denitrification takes place here. So this is essentially the first stage of the process, and then we go to a second stage. So majority of everything's removed here. Second stage again is important for polishing and also to make it the most economical and most effective systems to do it in 2 stages. You may need an external COD source coming in, possibly in the second stage, maybe even in the first stage. I'll kind of touch on that. Jason did touch on that in regards to the COD BOD ratio versus the nitrogen ratio. And then you've got your last aeration denitrification stage. And from there, you go into your membrane basin, which is essentially your liquid solid separation. Your solids typically go back to dewatering, and then your liquid can go to discharge, or it can go back to the front of the system for dilution purposes. And just a visual on that. So we have an aeration basin here, and then we have an empty membrane basin. So here are flat sheet membranes. You can use hollow fiber membranes as well. We use both depending on the application and the supply availability. But again, these membranes then are submerged, and this is where you have the liquid solid separation part of the process. Some examples, just to get, that GW has quite a bit of experience here. This is the Stormfisher project in London, Ontario. GW did this back, I think, in 2014, somewhere around there. So roughly, it's been operating for roughly 10 years now. Here's 2 thermophilic digesters. They feed the digestate holding tank or post digester. We have gas storage here. From here, it goes into the aerobic basin, and then liquid solid separation is the membrane basin, which in this case is a submerged concrete vault. The membranes are in here. Here's pumps and blowers in here for weather protection and such. Very nice system, but after several years of operation, they actually did find a partner to take the Digestate. So I was last up there about 18 months ago, and they weren't operating the system at all. It was completely mothballed, and they had a good arrangement in place, even up in Canada, for them to haul off the Digestate all year round, and it allowed them to shut down that system, which of course is a significant operational cost savings. But again, they have it, so if that deal ever falls through or they have problems, they can start it right back up in a matter of days or weeks. Another project that has the same 2-stage nitrification denitrification process to meet dilution water requirements as well as discharge requirements to the permit is Quantum Biopower up in Suffington, Connecticut. I believe this was started up in about 2018, 2019. So they've been running, roughly 5 years now. And again, the complete design, supply, and engineering was all done by GWE. So digestate treatment objectives, again, primarily to meet your discharge limits, keep your plant operational. If you can't get rid of it on the back end, you can't bring it in on the front end. Again, typically with these food waste digesters, there is some dilution required. Depends on your balance of your feedstocks, and that requirement's going to wax and wane. But you cannot continue to throw water back to the front that has high level of nutrients in it, because you're going to end up reaching a toxicity level and causing operational problems within your digester. These are just some typical permit ranges that we've seen for BOD and TSS. I'm not going to talk about that because those are all taken care of in this process quite easily. And then the nitrogen and phosphorus ranges can be maybe 10 to 40 milligram per liter, phosphorus 5 to 20. Again, you can see some extremes on either side of that, but this type of process, we can design it to meet whatever your discharge requirements are, even if it needs to go to water course. In other words, a direct discharge MPDS permit. So it's all achievable. Again, the nitrogen removal, we went over the nitrification, denitrification. Essentially, post anaerobic, all your nitrogen is essentially converted to TKN. Most of the organic nitrogen remains with the solids at the dewatering liquid solid separation step. The ammonia nitrogen, which is soluble, stays in the liquid, and that's really what we've got to address in the aerobic process. The literature again and experience, you need 3 kilograms of BOD is required to biologically remove 1 kilogram of nitrogen. In the industry, we like to refer to COD better because it's a much more reliable measurement, and it's something you can do in the field much quicker. So we typically talk about how much COD is required to remove a given part of nitrogen. So depending on your BOD COD ratio, that's going to put you maybe somewhere around, six parts COD to 1 part nitrogen. I think a good range is 6 to 8. You probably don't want to be below 6, and 8 is typically comfortable. And again, in this process, you can be well above 8. It's not going to cause you any problems necessarily, as long as you meet your BOD discharge limits. But we're not limited so much on the high side. It's really more limited on the low side of the minimum amount of COD you need to get that biological removal of the nitrogen. Another term that you'll hear is your sludge loading rate, or SLR, and that really refers to how much nitrogen is being uptaken by your biomass. So that again is typically a ratio of nitrogen per kilograms of mixed liquor volatile suspended solids. And one thing of note is it's very temperature sensitive. So depending on temperature, you can range from 0.1 down to 0.001 kilogram of nitrogen per day of VSS. So that's a huge range. And if you pick your operating temperature wrong and you miss it, you could be having a situation where you're not getting as much nitrogen removal as you need. So you got to pay attention to the temperature in your design and any seasonal fluctuations to make sure that you account for that, either from a tank insulation standpoint or having the capacity to be able to function properly at lower temperatures. The other typical contaminant of concern on the nutrient basis is phosphorus removal, as the other speakers spoke about. Typically, most of it's chemical precipitation. Again, your total phosphorus is going to vary depending on your feedstock. So maybe we're looking at maybe 150 to 300 milligram per liter is not uncommon in food waste digesters. Typically 70% or so can leave with a sludge cake, at the digestate liquid solid separation standpoint. Then the balance goes to the aerobic process, and that's what we need to account for in our design. Plus or minus 50% of this that makes it through is going to end up in the aerobic sludge. What's left, a small percentage of that, is going to be precipitated by the ions that are present in the wastewater. So all water is going to have certain levels of calcium and magnesium. So you'll get some, let's say natural precipitation just based on water chemistry. And then the balance of that needs to be removed in order to be underneath your permit limit. You need to take care of that with the addition of ferric chloride. So you make basically you precipitates it out into an iron phosphate, and essentially removes it from the stream, and then you can go to discharge or again recycle to the front of the system. What we're talking about doing here is again precipitating inorganic materials into the biomass. So it's important to understand if you have high levels of phosphorus coming in, you're gonna precipitate out, and it's also going to displace your active biomass. So we have a VSS to TSS ratio that you need to be aware of. So when you go into chemical precipitation by adding ferric chloride, you could drop your VSS TSS ratio easily by more than 10%. And if you drop it too much, again, you're displacing the active biomass, and then you have less your waste, food to waste balance is offset, and you end up with not enough active biomass to achieve the treatment requirements that you need. So again, something important to consider on the design side. All right, from again, a little bit closer view, I apologize, it's a little bit difficult to follow here, the fine print, but to just, again, here's two thermophilic reactors. They discharge into the digestate holding tank or post-digester. From here, we take it to the dewatering system. Chemical addition, polymers are required at this stage. And then we go to the next step in the process where it goes into the dissolved air flotation system. Again, we target to be less than 200 milligrams per liter coming out of the DAF. We can probably be well closer to 100 milligrams per liter or less in normal operations, but what we give some buffer there. So we design based on 200 milligrams per liter from the DAF unit. And then from here, we have a little bit of a holding tank. It's pumped up into the first anaxic zone, for your nitrification. And then again, the second stage denitrification, and, an aerobic process. And again, we have mixing here as well as mixing back and forth between these tanks. There's a significant amount of recycle happening within this system. So that's essentially your stage one, and your stage two is essentially repeating this, but at a smaller level physically. It's a smaller tank, and less aeration is required. From there, again, the treated water goes into the membrane basin where liquid solid separation takes place, and then the permeate goes to discharge or to reuse, and then the solids are sent back to dewatering. This is another facility that's currently under design that'll go into construction as soon as it warms up a little bit. But again, here, as part of the site, here's your digestate holding tank. The digesters are down at the bottom of the page. From here, we feed into two screw presses. The permeate or pressate from the screw presses goes to the DAF. Clarified water goes to the front end of the process. So here is, we use the concentric tank design here. So our anaxic zone is around the outside of the tank. And we have a submersible mixer here, as well as mixing pumps, if you would, in the wall to move the water in and out through the system. So again, we got your nitrification in the anaxic zone, denitrification in the aerated zone. And again, we go to stage two, again, anaxic, nitrification, denitrification. And then from here, it goes to the membrane tank. So some takeaways, it's quite important to have kind of a belt and suspenders after your dewatering system. You really want to keep the anaerobic biomass from entering the aerobic system, because it's just going to bring a lot of COD, a lot of nutrients, and really kind of raise havoc or cause you to have to over design the system. The other thing to keep in mind is don't underestimate your COD conversion, right? At GW, we're typically conservative in our design, so we estimate a certain amount of conversion. In other words, how much COD in the digester is going to be converted into biogas. We generally expect to get more than what we design for, but we plan for that on the aerobic process, because what happens, the more substrate you convert into biogas, the more nitrogen you release. So as your COD conversion rate improves, which is what you want to do to produce more biogas, you're also liberating more nitrogen into your system. So you just need to be aware of that in your design. And this is something that we're quite familiar with. Again, pay attention to seasonal temperatures. You're going to see changes in your sludge's ability to take up nitrogen, the nitrifiers and such. So again, that's got to be considered in your design. From a dosing of your ferric chloride for your phosphorus precipitation, you typically want to do that in stage two. So in stage one, you want to allow kind of the naturally occurring minerals, if you would, in the water, the calciums and the magnesiums and such, to precipitate what they can as an iron salt in the first stage, and that'll reduce how much ferric chloride you need to put into the second stage. And you've got plenty of retention time for that to happen in that last stage of the process. So it's the best way to minimize your use of your ferric chloride. And again, lastly, just be understood about your VSS TSS ratio. As you drop out more phosphorus and such into your stream, you're going to displace your active biomass. So you just need to make sure you keep a healthy ratio as you go through the mass balance and design of your system. So that's what I have for you today. So a lot of information in a short period of time. So appreciate your attention.
Yeah, nice job, Brian. Thank you. Suddenly, biogas people are turning into wastewater treatment experts here.
And that's what we bring to the table. So we're already there.
A lot of different approaches. So we'll let you go. Thank you. And for the 119 of you still on the presentation, thanks for sticking it out. We've got one more talk. So this is GWT. We're going to talk about algae. So I'm going to introduce Martin Gross. So Dr. Martin Gross is a president and a founder of Gross Went Technologies. GWT is a next generation wastewater treatment company that has commercialized the revolving algal biofilm treatment technology, the RAB. Martin was one of the inventors of the RAB system alongside his other co-founder, Professor Zizhu Wen. Prior to founding GWT in 2016, Martin attained dual doctorate degrees from Iowa State University in the fields of bioprocess engineering and food science and technology. Gross also serves as a professor of entrepreneurship at ISU and serves on the board of directors at the Algae Biomass Organization and the Iowa Biotech Association. So with that, we're going to get the message about algae. Martin, the floor is yours. Thank you.
Sounds good. I imagine you can see my screen.
All set. Yep.
Awesome. Well, thanks for having me, Paul. Thanks for everyone that stuck it out to the last presentation today. I'm going to shift gears a little bit and talk about algae-based nutrient recovery from wastewater. So a little bit different than, let's see here, my screen just went black. Let's try this again. Right. Let's try this the old-fashioned way here. I need to keep out of presentation mode, so I don't know what's going on there, but we'll make this work. All right. We'll keep out of presentation mode because something was happening there. So we're an algae-based wastewater company, so removing nitrogen and phosphorus from wastewater using algae. So compared to bacterial or chemical or mechanical approaches, which you've heard a lot about today, we use microalgae. So think of a microscopic plant removing these nutrients from the water. The big advantage of using algae versus bacteria or chemicals is it's unique in that it removes both nitrogen and phosphorus at the same time using the same unit process. If you're going to remove nitrogen, you'd use bacteria like was just talked about, or chemicals for phosphorus. So algae is unique. You can do both at the same time. It's also unique in that it has a really nice carbon footprint sustainability story associated with it, in that it uses about a third of the energy to remove nitrogen compared to the aeration processes that you just heard about. And it also, since it's a microscopic plant, it's able to actually consume carbon dioxide from the atmosphere. It uses carbon dioxide as its carbon source as it grows, so it actually can reduce carbon footprint, and that's done by the algae as it's respiring or growing. Carbon's captured and consumed by the algae through CO2, but it also is able to reduce your nitrous oxide emissions from an aerobic process like what you heard before. So all in all, able to reduce carbon footprint, low energy, recover nitrogen and phosphorus at the same time, and then hopefully reduce costs associated with treatment. So you may or may not have heard about algae or GWT in the past, so I thought I'd give a quick snapshot. Really just to show that we've been doing this for over 10 years now. We have about $14 million in projects under construction with another $27 million in design. So algae being a newer technology, we always get the question if we're commercially deploying systems or not. And the answer is yes, we are deploying systems. So we're actively looking for projects. So a little bit about our technology specifically. It's called the Revolving Algal Biofilm System, or RAB or RAB, people will call it. And essentially, it's vertically oriented conveyor belts where the algae will attach and grow on the surface of these conveyor belts. And as those algae are growing, it's actually eating the nitrogen and phosphorus from the wastewater, and that's the mechanism for removal. There's some nitrification, denitrification going on as well in the process, but largely, it's algae growing and cleaning the water. And again, as that algae is cleaning the water, it's consuming CO2 out of the atmosphere. And then periodically, we scrape the algae off the surface of the belt. And we take that algae and make it into a variety of different products. And I'll talk about those in a minute. So again, another differentiator between bacterial-based or chemical-based nutrient removal, we're producing algae, which is valuable. So at the end of an aerobic process that we just talked about, you're producing a bacterial sludge that's a cost to dispose of one way or another, or a chemical sludge that needs to be disposed of. So it's a cost to the project. When you produce the algae, it's actually a revenue stream for the project. And we take that algae and make it into fertilizers and plastics and as well as biofuels. So let me play just a video here. This is what a commercial facility looks like. This is a 3-belt modular system. You can see it's all positioned within a greenhouse. Our system is these vertical conveyor belts that are slowly rotating in and out of the wastewater. They're moving really slowly, low tension, moving parts, but the parts that are moving are sprockets and chains at low tension, low speeds. So the actual upkeep on these systems is pretty simple. What's being shown on the screen now is the harvesting mechanism on the algae system. So periodically that algae is harvested and that mechanical scraper just comes by, scrapes it off the surface. And then that algae gets sent to central collection before we'll come and collect that algae and buy it back from you. So again, vertical conveyor belts, algae rotates, algae attached on the surface. As the algae grows, it's consuming the wastewater or the nitrogen phosphorus from the wastewater. And then the algae is harvested. And as the algae is harvested, it's actually removing the nitrogen phosphorus from the system in the algae biomass. It's all positioned within these reservoirs. They're low depth, about 1 meter or 3 feet deep reservoirs, and positioned within a greenhouse. So we sell the system in modules. So this is what a commercial module looks like dimensionally. They're about 10 feet tall, about 10 feet wide, and about 100 feet long, roughly. The whole system is driven off a 5 horsepower motor. So again, very low energy system compared to bacterial-based, aeration-based systems like what we just talked about before me. Again, using about 1/3 of the energy. So one of the challenges with aeration-based nitrogen removal is a lot of energy input, so that's a cost. You're producing sludge, bacterial sludge, which is a cost to dispose of. And you're producing a huge amount of nitrous oxide emissions. So from a carbon footprint perspective, from an energy perspective, and a useful product perspective, algae systems have advantages. Obviously, these bacterial systems have been around for years and years, really reliable, do the job well. Capital costs generally are slightly lower than our system. Operating costs, our system's lower. So there's some trade-offs, and different projects may need a bacterial system or an algae system. Depends on what's important to the client and the customer, capital, OpEx, or 30-year cost of the system. So again, the previous slide was a module. This slide here showing what it looks like in a commercial deployment with multiple modules. So this is our project in Pasco, Washington, treating a 4 million gallon per day digestate stream at a food processor. So what's being shown here is just an example of how these modules are stacked side by side. This project specifically needed 13 modules, so the water actually flows in and goes through this in series. So it'll actually come into this open reservoir first and then flows through stage by stage until it gets to whatever treatment target you're focusing on. So we've done about 40 projects now over the past 10 years. A lot of in the Midwest. We've initially as a business focused on municipal projects, specifically municipal digesters. Since then, we've really found that a niche of ours is industrial food and waste digesters. The algae grows incredibly fast. We get really good treatment rates on food and beverage digestate. So this is a prime target, and I know many of the folks on this call are looking at these type of digestion projects. So food and beverage is a really good application for us. Whether it goes through a digester and then our system for nutrient polishing, and then to a municipality or a treatment district, or direct discharge, we can do either. So we have projects where we're discharging directly into the environment after our system, and then others where it's going back to a municipality. We also do anaerobic digesters at municipal treatment plants. So there's something called as anaerobic digestion side stream in these projects, where basically all the bottom solids from the aerobic and primary clarifiers are going to a digester, and then we would basically pre-treat that digestate before it goes back to the headworks. Creates an exit for both nitrogen and phosphorus here. And then lastly, we've done these agricultural waste projects as well, where we can treat the water before a holding cell or land application to remove nutrients. So what's the differences and advantages of an algae-based system for digesters compared to conventional bacterial or chemical? First of all, we're doing both nitrogen and phosphorus at the same time. So within the same unit operation, we're removing nitrogen and phosphorus. Not noted here is BOD. So if there's BOD that remains, we also can treat that. We treat nitrogen, phosphorus, and BOD as well, all at the same time in the same unit process. So if you do need more than just one of those pollutant treatment, it may make sense for you to use a system like ours, which can do it all in one unit process. Next is it's a simple and low cost operation. So in the previous presentation, there's talk about all the parameters that are required for effective aerobic nitrogen removal. There's several things in controls and processes that need to be controlled to make the process work effectively. Ours is really a set it and forget it type system. Water flows in, and it's designed so basically water flows in, goes through the system. As it comes out, it's going to meet its treatment target. You're not messing with DO or VSS or solids retention time. It's all a very simple operation. So low skilled operator as well as low skilled technician to maintain the equipment on our system. Just chains and sprockets and bearings that need to be maintained, all easily accessible above the water level. I actually separate potential CI score reduction for a biogas project as well as greenhouse gas emission offset. I separate those two because certain types of projects we've worked with eco engineers and demonstrated that within the current framework for certain types of projects, we can actually lower the CI score with our system to improve the value of the gas. Other type of projects, we just aren't within the existing framework. So that's where it's potentially reduced CI score. So it's project dependent there, but all projects were able to offset greenhouse gas emissions. So we're offsetting greenhouse gas emissions in a number of ways. First of all, algae, as it's growing, it's actually capturing the carbon dioxide during the treatment process because it's a microscopic plant. So for every ton of algae that we produce, we're consuming 2 tons of CO2. So it's pretty easy to account for. Next, we're using less energy than the conventional aerobic type process for nitrogen. Less energy means lower carbon footprint. Third one is that nitrous oxide emission. So one of the byproducts of removing nitrogen with bacteria is the production of nitrous oxide. And that's a huge greenhouse gas contributor. It's about 273 times more potent than. Okay. Yeah, just a couple more slides. Just talking about the end use of the biomass here. So algae gets harvested off our system and has value. Our primary product is this slow release fertilizer product on the far left. We're also working with a bioplastics company to take that algae and make actually foam insoles for shoes. And then the third product is a soil amendment. So you can see varying levels of value between those products. Again, our primary one today is turf grass fertilizer, but there's obviously more opportunity, more value in other products. The last one on the far right is aviation fuels. So we just partnered with a global oil major that's really interested in making algae into aviation fuels. There's a big demand for feedstock for aviation fuels. I know there's a lot of energy companies here too, so I thought I'd dig into that a bit deeper. This is the real opportunity and the really cool story that we can do as an industry is produce biogas, but also create a feedstock for aviation fuels, which is a huge demand. So just digging into that real quick as we wrap up. Basically, sustainable aviation fuels or SAF are in high demand. But the problem is that there's not enough feedstock to make as much aviation fuel that the world needs, or the targets that are being enforced by the airline industries. So you might, in the United States Department of Energy, put out a report basically saying, hey, we have this feedstock gap, and that algae needs to play a major role to feed the feedstock gap to make the aviation fuel targets a reality. And really what that's happened is global oil majors like Total and Chevron, for example, are investing in algae. And that's what I'm showing in those bottom graphics, investing in algae to create that feedstock supply. And we're active in these projects. And really what's exciting to me is there's a demand for the algae, but the real value that we're providing is nutrient treatment for these digester projects. And we can actually supply the aviation industry, the algae supply into these markets. So happy to talk about that and where we are, but have a partnership with an oil major to start developing this. The last project is just a project example for us. This is the project with Pasco, Washington. This is 5 industries and industrial park in Pasco. This is in Washington State in the Tri-Cities area. They needed to remove nitrogen specifically, putting in new greenfield digesters to treat their waste before land application. They have these Evoqua low-rate digesters there. And then they are putting the algae system on the back end of the digester for nutrient removal. So this is project currently under construction, start up later this year. You can kind of see what this looks like on site compared to the large footprint digesters. And again, our focus on this project is nitrogen removal. This is what the project looked like, at least in November. So it's well underway in construction. This is a 13 module project for us, about 4 million gallons of wastewater per day of flow, removing over 2,000 pounds of nitrogen per day. And then when we put the project through our accounting model, we're able to demonstrate that the system is able to remove about 5,300 metric tons of CO2 offset per year compared to the conventional technologies. All right, that's all I got. Thanks again for the opportunity, Paul.
You're welcome. A couple questions before we call this. So what's the NPK of your dried algae fertilizer?
Yeah, so NPK for a fertilizer is generally 8 to half.
8 to half.
8 to half. Yep.
Cool. There's no ammonia inhibition upper limit here. You can just kind of take 2,000 ppm, no problem.
Yeah, so there's ammonia toxicity in algae at a certain level. So certain projects like these dairy waste projects have 2,500. We can't just do this in batch where you're providing the algae system 2,000 parts. You either need to manipulate pH to lower the free ammonia concentration, which can be controlled. You can control your feed rate, and that's usually the way we do it, is we control the feed rate. So in our basins, we're never at that 2,000 concentration. We're recycling back to dilute. So it's something that we look at specifically on projects that have ammonia concentrations over 400. Really is probably where we want to keep track of it, and just put in a control strategy for pH and maintain a free ammonia concentration at the. Yep.
Thanks, Martin. Great job. Wonderful technology. Just pretty easy peasy, right? You just kind of put it in, it just kind of runs. So that Slater, Iowa project is pretty cool. If anyone wants to go look at it, it's a nice, clean design. Good. We'll let you go. Thank you for your support. Thank you, all 95 of you that stuck it out. Look for your email from me. The slides are up on my website, green-tech.com, but you're going to get an email with that link coming your way. And thank you for your support. We are wrapped.